All right, let's jump right in. We're going to tackle a question that honestly sounds like something you'd dream up late at night, but it's actually happening at the absolute forefront of quantum physics.
I mean, really, what happens? You take the simplest atom there is, right? One proton, one electron, and you somehow force it to live exclusively on the surface of a donut. How would it even act? It might sound like just a fun little puzzle, but the answer, well, it might just unlock a completely new way to build the quantum technologies of the future. So let's get into the setup. How in the world did scientists even begin to wrap their heads around this?
Well, it all comes from a brand new theoretical paper that just came out. Researchers crunched all the numbers, and they had to combine quantum mechanics with the really complex math of curved surfaces. And what they discovered, it actually changes some of the basic rules we thought we knew about hydrogen.
You see, to figure this out, the researchers couldn't just pull a standard textbook off the shelf. No way. They basically had to write a new rulebook, one that merges three very different ideas into one. But first, a quick bit of terminology, just so we're all on the same page. In math and physics, that classic donut shape is called a torus. So when we're talking about an atom on a donut, we're really talking about an atom confined to a toroidal surface.
Okay, so here are the three main ingredients they had to mix together. First, you've got the weird, curvy geometry of the torus itself. Second, you have the good old-fashioned electric attraction between the proton and the electron. That's standard stuff. And third, they imagined hitting this whole system with an unbelievably fast laser pulse. And I mean fast. We're talking attoseconds. A billionth of a second. Now this is where it gets really interesting. Just the shape alone has a huge effect. Even with no other forces at play, the curvature of the torus creates this kind of invisible potential. You can picture it as a gentle slope that basically encourages the electron to hang out more on the wide outer part of the donut and stay away from that cramped inner hole. This geometric potential is the first big hint that things are about to get strange. And all that strangeness leads directly to the first major discovery. Because when they solved all the math, they found the atom's energy levels were completely jumbled up, creating something that was, well, totally unexpected. Let's just put them side by side for a second. On the left, a normal hydrogen atom holds onto its electrons super tightly at an energy of negative 13.6 electron volts. But look at our donut hydrogen on the right. It's way more loosely bound at only negative 2.79. The shape itself actually weakens that bond. And you can also see that while a normal atom's energy levels bunch up, the donut atom's levels organize themselves into these distinct, separate bands. But you know, that wasn't even the biggest shocker. Not by a long shot. The team found a feature in the energy spectrum that, in the normal hydrogen atom we learned about in chemistry class, simply has no equivalent. It just shouldn't be there. And this chart shows it perfectly. Down at the bottom, you've got the bound states. Those are the energy levels where the electron is still stuck to the proton. Way up at the top are the unbound states, where the electron has enough juice to fly off and escape. But look right there, in the middle, there's this huge empty gap, a forbidden zone where no energy states are allowed to exist at all. And the key thing here is that this isn't some tiny little gap. It is a massive 4.898 electron volt chasm carved right out of the energy spectrum. And its size is determined directly by the donut's geometry. It is a physical fingerprint left by the shape itself. So the geometry changes the atom's fundamental properties. But that's not all. It also opens up these incredible new ways to control the atom. And that's where things really start moving. The researchers figured out that if they zapped the atom with that ultra-fast laser in just the right way, they could kick the electron into a state where it doesn't just sit still. No, it actively starts circulating around the big loop of the donut. It creates this tiny, incredibly fast electrical current. They essentially turned the torus into a quantum racetrack for a single electron. So what does that even look like? Well, at the quantum level, the electron isn't a tiny ball. It's more like a wave of probability. In this picture, you can see that wave is all bunched up at one spot on the racetrack right after that laser pulse hits. And then it's off. That little packet of probability starts racing around the torus. Here you can see it halfway through its first lap. And this isn't random. It's a predictable wave traveling on a closed loop over and over again. And it is moving at a speed that is just hard to comprehend. One full lap takes just over 30,000 attoseconds. Now, to put that into perspective for you, there are more attoseconds in 1 second than there have been seconds in the entire 14 billion year history of the universe. It's just unbelievably fast. Okay, so we have a new kind of atom with this weird forbidden energy zone, and we have a quantum racetrack. What's the point? Well, this is where it all comes together into a powerful new idea: engineering with geometry. The study found you have this amazing level of control. So let's say your goal is to make the electron race around the big main loop of the donut. The tool for that is a laser pulse that's lined up with that flat plane. Now, what if you have a different goal? What if you want to excite the electron around the smaller tube-like loop? Easy. You just rotate your laser 90 degrees so it's aligned vertically. It's like having different keys for different quantum doors, just by changing the direction of your light. And this is why this is such a big deal. It's not just a scientific curiosity. This is practically a blueprint for how to build quantum devices by designing their properties right into their physical shape. The geometry itself becomes the engineering tool. Think of it like a whole dashboard of tuning knobs. By changing the donut's overall size or how thick the tube is, you can precisely control everything. You can dial in the exact size of that forbidden zone. You can set the speed of the electron on its racetrack. You can choose which energy levels are allowed. You can even fine-tune how the atom interacts with light. Which leaves us with this final, really provocative thought. For decades, the search for new quantum technologies has been all about discovering exotic new materials. But what if this research is pointing us down a totally different path? What if the next great leap forward in quantum engineering isn't found in complex chemistry, but in the simple, elegant power of geometry?